Let's begin. Welcome back to asymptotics and perturbation methods. So today our topic is a very clever old technique called the method of stationary phase. Old because I think it may actually be one of the first methods used in this context. I should have checked this out. I sort of think it was invented in the 1800s, maybe by Lord Kelvin. I don't know. In any case, it's a pretty fun technique that is used when you have an integrand that's rapidly oscillating. So I'll clarify what I mean in the course of our discussion, but we saw last time that Laplace's method gave us a way of estimating integrals when the integrand was sharply peaked, right? It was a narrow bell-shaped sort of thing as some parameter goes to infinity. And so the integral was dominated by the contribution coming from the neighborhood of that one point under the peak. Here, we're going to see something similar in that an integral is going to be dominated again by the neighborhood of one point, except here it'll be a point where rapid oscillations in an integrand suddenly slow down and become stationary. So away from that point, you get a lot of cancellation because of the rapid oscillation. But at the point of stationary phase, that cancellation effect breaks down, leading to a big contribution. So that's the intuition. Let me share my screen with you. So the big payoff for today will be using the method to asymptotically approximate the famous Bessel function J0. All right, so let's see here. I'll share like this. Oh no, I don't want to do that, excuse me. After all this time in the COVID era, I should know how to share my screen. I'm going to try this again. Okay. There. All right. So method of stationary phase. If you want to read about it in Bender and Orsag, that would be in section 6.5. And as I said, the method is really tailored to dealing with integrands that oscillate rapidly. So I've written out a lot of preliminaries here because I think there is a fair amount of writing in this lecture, and I wanted to just get this out of the way. This is not really yet the method of stationary phase. Once we get to that, I'll start just writing in real time. Okay, but anyway, hopefully this is manageable. All right, so the first remark is just think about this kind of trivial integral, just integrating cosine of omega t. But what I'm trying to drive at with this example is to underscore the idea of what it means for a function to be rapidly oscillating. So you see here, I've got a lot of waves packed into the interval a to b. And what I'm trying to indicate by coloring in this little piece here is that there's just as much positive stuff on this side as there is negative stuff on that side. And so those two contributions will tend to cancel. And so you can see that when you evaluate the integral analytically, of course, we can do it exactly. It's just the integral of cosine. So we're getting 1 over omega sine omega t. And then evaluate it between these two endpoints, a and b, which are not necessarily any multiples of pi or anything like that. They could be any old points. You get this exact answer, 1 over omega, and then a difference of signs at the endpoints. And the key thing is that as omega goes to infinity, that is going to 0. That integral is going to 0, like 1 over omega. It's big O of 1 over omega. And intuitively, that should make sense because what's happening is, 1 over omega sets the scale for the it's the period. 2 pi over omega would be the period of the oscillations. And so to the extent that the waves don't exactly cancel out their contributions, they will tend to make an error on the order of one of these spacings, something on the order of 1 over omega. So that's the intuition for this kind of integral, that you get a lot of cancellation, and the amount that doesn't exactly cancel is going to be of the order of one of those waves, 1 over omega in width. All right, so that's the first bit of intuition for rapid oscillation. Now, none of that really changes if instead of having a constant amplitude, suppose we have an amplitude given by some slowly varying smooth function f of t. So that's shown here in this orange. That defines a changing amplitude that changes slowly in time, slow compared to the oscillation frequency. And so if I have some integral that looks like this, with the f of t multiplying a cosine omega t, that kind of thing is also going to have the same asymptotic behavior as omega goes to infinity. You would again expect the integral to decrease like 1 over omega for omega tending to infinity for the same reason, because you get a lot of oscillatory cancellation. So we could confirm that by bringing integration by parts out of the tool shed. We discussed it a couple lectures ago, but remember the idea that, like, since we're dealing with f of t cosine omega t, if we want to integrate by parts, let's write cosine omega t as d dt of 1 over omega sine omega t. So with that trick, now we're all set up for integration by parts. This is like a function d of something else. So we get this function times this as the boundary term at a and b. And then we have to subtract this term 1 over omega and then sine omega t inside the integral times the derivative of this piece. So there it is, f prime of t. And the hope is that this boundary term will be the dominant contribution. Notice, by the way, it's of order 1 over omega, as expected. As long as we don't have f blowing up at the endpoints, or in fact, if we want this to be the dominant term, we better hope that f is not 0 at the endpoints. So I'm going to assume f is both finite at the endpoints and that it's not 0 at both endpoints. So if we have all of that, then we could expect this to be the dominant term. And this term will be strictly smaller asymptotically because it already has this prefactor of 1 over omega. But we expect this integral itself to be small when omega is large by the same kind of reasoning that I just gave, that it'll be all chopped up by the fast oscillations of sine omega t. So this will be correct if this function f prime of t is itself well behaved. I'm not going to say too precisely what I mean by well behaved. I will in a minute. But for now, well enough behaved that we can estimate that this integral will go to 0, then multiplying the 1 over omega makes this whole term strictly little o of 1 over omega compared to this one over here, which is big O. All right, so again, putting in this modulation in the amplitude doesn't really change anything. We still get the kind of behavior we expected intuitively. So all of this can be put on a more rigorous foundation through something you may have learned about in an analysis course called the Riemann Labaig lemma. So the Riemann Labaig lemma in the version that I'm going to use here would say that if this function f is absolutely integrable, meaning if I take its absolute value and then I integrate it from a to b, that doesn't blow up. So if this integral exists and it's finite, that's a pretty mild condition on f. I mean, f could be discontinuous or fairly nasty. As long as it satisfies this mild integrability condition, that's enough to prove that this integral will go to 0. If I multiply the f by an e to the I omega t with a rapid oscillation, a high frequency omega. So I'm not going to prove the Riemann Labaig lemma, but that gives you the flavor of, I mean, it's sort of a theoretical foundation for why what we're saying should be true. And actually you can prove something stronger, which is that if the f prime, the derivative exists and is finite on this whole closed interval, then you can prove that not only does this integral go to 0, but it does like big O of 1 over omega. So, so it's just what we would expect from our formal manipulations with integration by parts. All right, so this is some of the background that I just wanted to bring up. We haven't done anything with stationary phase yet, but let me keep on cranking along here to now start writing some stuff in real time. So now we're going to generalize to the case that we want to spend the rest of the discussion on, which is integrals now of the form where I've got this modulation function again, think of it if you want as some continuous f of t or maybe smooth f of t times, instead of e to the I omega t, it's now going to say e to the I x times some function of t that we'll call psi of t. So that's the generalization. It used to just be t, now it's psi of t. So here we're supposed to be thinking of x going to infinity. And I'm using the notation we've been using throughout the course, that x represents our large parameter, whereas a few minutes ago I was calling it omega. So we're going to, rather than thinking of this as a large omega, the earlier omega notation. And I'm also going to use psi of t generalizes the earlier t. Okay, so what does that do for us? Well, okay, so we would like to estimate this as x goes to infinity. And let's try naively just doing integration by parts to see what we would expect. So applying parts to this, well, actually, maybe I should say one little thing. Just in case you're not super familiar with complex exponentials, I'm just making, maybe we should write this out, that this e to the I x psi of t is cosine of x psi of t plus I sine x psi of t. So just to remind you that there is this oscillating function built in there through the e to the ix term. Okay, but anyway, so now let's try to estimate the integral. Let me move this down here. All right, so if we integrate by parts, then we would say I of x is, all right, so our trick will be, just like we earlier wrote cosine omega t using a derivative of sine omega t, we can do something similar. We're going to write I of x as a boundary term, f of t, e to the I, x, psi of t. So that's playing the role of the earlier cosine. And then I'm going to divide that by ix, psi prime of t. That's getting, so maybe I should just write off to the side. What am I doing here? I'm looking at integral from a to b, f of t, and then I'm just manually putting in a d dt of e to the I x psi of t so that I can integrate by parts, but that will introduce a term ix psi prime of t. So I'm putting that in a denominator to compensate that whole thing dt. This is my I of x integral, just written in a way that's set up for integration by parts. So anyway, recognizing that, then I get this term, the boundary term, where I'm looking at t equals a and t equals b. So that goes up there. And then I have to subtract off minus 1 over ix. And then the other term in integration by parts, I'm going to have d dt of, let's see here. So I've got to put the derivative on the f over psi prime. I already took the ix outside. And then I'm left with an e to the I. Looks like I want to move the whole thing to the left, give myself a little more room. Excuse me, I don't want to go off the edge of my page. Let's do that. And then times e to the ix psi of t dt. There, that should be right. How's that looking algebraically? You see what's happening? Yeah, okay. So then, let's stare at this. Again, I have the two terms. Maybe I should circle them and discuss them separately. So there's this term. And that term, by a kind of generalized Riemann Labaig argument, well, I mean, it would require a little bit of generalization to what I was calling the Riemann Labaig lemma. We would expect that this first term is still going to be big O of 1 over x because of this 1 over x term sitting here. And the second term is little o. Of x. That is, what I'm saying is if the integrand in that expression is well enough behaved, then we've already got the 1 over x outside, and then we expect that integral to be asymptotically smaller than the boundary term. So I'm not going to justify that except to say, of course, we'll need some conditions for that to be true. So if, let's look at what could potentially cause trouble. First of all, there's this f over psi prime that we see we're taking a derivative of right here. We also have to worry about it here, f over psi prime in the boundary. So we want that thing to be well behaved over the whole interval so that there's no problem taking its derivative and doing that integral. So let's say that if that is smooth, or I'll be sort of vague about what I mean by smooth enough on the closed interval AB, and we don't want it to be 0 at both endpoints. Right, because if it's 0 at both endpoints, then when we evaluate this expression, we're going to get 0, and so this cannot be the dominant term, the boundary term, because it's 0. So in order for it to be dominant, let's suppose it doesn't vanish at both endpoints, which will be typically what will happen. It will not. And it's smooth enough on the interior. Also, just for technicality's sake, I'll mention that we're also going to need psi continuously differentiable. After all, I'm going to be taking its derivatives. So I'd like it to be continuously differentiable on this closed interval. And I don't want psi to be constant on any subinterval. If psi were a constant somewhere, then psi prime would be 0. on that interval, and I'd be dividing by 0 in a big way in here, which looks like that could cause trouble. So anyway, it's not really, you know, my usual thing to be too precise about the assumptions. I'm just throwing those down because I want to bring out the point about, now we're getting to the meat of today's lecture, which is, you can see where psi prime equals 0, that could potentially cause trouble. We keep talking about, what if psi prime is 0? We're dividing by psi prime in a lot of places. So let me raise that question now. So what if psi prime equals 0 somewhere in the interval? I mean, earlier I said it shouldn't be constant on a subinterval, but what if it's just 0 at one point? Psi prime equals 0 somewhere. I'm highlighting that because this is the issue with stationary phase. A point of stationary phase is going to be a point where psi prime is 0. So let me try to explain why that's of so much interest. So the points where psi prime of t equals 0 are the points of stationary phase. So in that language, the function that I've been calling psi is what's considered the phase. Psi of t is often called the phase of this expression e to the I x psi of t. But really, in fact, it's x times psi that's the phase. I mean, right, it should be the argument e to the I blah. The blah is the phase. But I won't make that distinction often. Because it's just multiplying by this parameter x. But okay, anyway, the issue is, what happens when one of those has a 0 derivative? That's where the major contribution to the integral comes from. So the major contribution to I of x comes from the neighborhood of such points. I'm also going to, in saying that, I'm assuming that f is not 0 at those points. I mean, that would be a real coincidence if simultaneously the phase was stationary, meaning it had 0 derivative there, and simultaneously the modulation function f also happened to be 0 there. That would be two things being 0 independently, simultaneously. That doesn't tend to happen. It could happen, and we'll discuss what will happen, what goes on in that case towards the end of the lecture, but typically it will not happen. So in a minute, I'll explain why the major contribution comes from the points of stationary phase, but I see I've got a couple of remarks in the chat to look at, so let me see what's going on. If we have psi equals 0 on a set of measure 0, asks Maria. So I said, what if it was 0 on a whole interval? Maria says, what if it's just 0 on a set of measure 0? Then the integral wouldn't be affected, right? And then Mark says, well, it could be. For example, 1 over x is only 0 on a set of measure 0, just at one point, but the integral is strongly affected. Maria agrees with that. So yeah, I'm not necessarily giving the best condition here. So I didn't want to get into any measured theoretic considerations. I'm just trying to give a simple criterion. By the way, there are books about asymptotics that are rigorous. And for instance, there's an author named Olver. I think it's Peter Olver. So if you wanted a rigorous treatment of the kinds of issues that I'm skipping over, would recommend his book. Olver. So that's just a little aside, since some of you I know care about these matters. Okay, but anyway, so let me get back to the explaining now. Why is it that the major contribution to the integral comes from the points of stationary phase? So, why is this true? Well, all right, so here we need to think a little bit about what I said earlier about the reason the integral is small in the first place is because of these rapid oscillations that tend to chop up the function into positive and negative parts. And so let's think about what happens to the frequency of those oscillations near a point of stationary phase. What we'll see is that the frequency slows down and actually becomes 0 at such a point. And so you lose the oscillatory cancellation to a large extent. So that's the intuition. You get the big contribution because the oscillatory cancellation effect disappears, or certainly weakens, near points of stationary phase. So let's see exactly why. Let's go into that in more detail. All right, so to see this, let's expand the phase function in the neighborhood of a point of stationary phase. Rather, I guess I should say expand it about. Let's expand it around some arbitrary point t0, not necessarily a point of stationary phase, but then we'll see what's special about that. So if I just expand around some point, psi of t will be psi of t0 plus, just doing a Taylor expansion, t minus t0, psi prime at t0 plus 1/2 t minus t0 squared, and then the second derivative. And we could go higher than that, but let's just stop at the quadratic term for now. Then when I pop that into the e to the ix psi, let's see what we get. So I'll have an e to the ix psi of t0 plus psi prime at t0, t minus t0. And let me not write the quadratic term right now because to make this point, I don't need it. What I want you to notice is that in that expression, psi prime of t0 is just a number, right? It's just a constant. It's whatever the derivative of psi is at this point t0. So this notice that it's multiplying something proportional to t. And so this plays the role of our earlier omega, sort of, right? It's an omega t type of term. So psi prime of t can be regarded as the local oscillation frequency. I mean, times this x. Don't forget that. So x psi prime at t0 is the local oscillation frequency at t0. That's what this little expansion shows us. And so very conveniently, I'm at the right place to show this diagram that I prepared ahead of time. In Mathematica, I made a little picture of a function that has a point of stationary phase. And so what you can see in this waveform is that, we have fast oscillations out here. But then they slow down. You can see there's a wider spacing, and the point of stationary phase is occurring right here. Where everything is slowing down. So the oscillations are much slower in here. And in particular, we're losing the oscillations altogether. I mean, we're just seeing something that's kind of slowly varying compared to this. You should be picturing this, in the limit of, I didn't want to draw it at extremely high frequency because the picture will look like a nasty mess. But if I had done that, these oscillations would be very fast up and down, whereas this would still look kind of gradual right here. And so that's going to dominate any future integral, this region. Notice, by the way, this doesn't necessarily go all the way down here. There's no reason why it would. I mean, this is just a place where the phase is stationary, but we don't know that the amplitude is maximum there. So it's going to be sort of at a less of a value than the surrounding neighborhood. Similarly, if I have an envelope, the same sort of scenario occurs. These fast oscillations follow the envelope. But then when I get to a place of stationary phase down here, again, have this slow oscillation, and I don't go all the way down to the envelope. Okay, so you can see that the oscillatory effect, the cancellation effect, is going to weaken at a point of stationary phase. And so that's going to end up changing the asymptotics of the integral. It won't be order 1 over omega anymore, or in our new notation, 1 over x. We're going to get some different scaling with respect to large x. And so that's what I want to work out with you now. I'll just sort of highlight what's going to happen. So we can show that if psi prime at some point c equals 0, but as would generically be the case, the second derivative will typically not be 0 there also. So if we have only the first derivative vanishing, but not the second, we're going to get that the integral will be of the order of 1 over square root of x as x goes to infinity, rather than 1 over x, which is what we saw earlier. Excuse me for a second. I want to look at my chat. Is it necessary for oscillations to slow somewhere in order for a stationary phase point to exist? Well, I'm not sure I understand the question. So we're defining a point of stationary phase to mean a point where psi prime is 0. And so at psi prime equals 0, the oscillations are slowing at that point. to zero frequency. So maybe I haven't understood the question. Do you want to elaborate on the question?
Oh, I was just wondering what would happen, for example, in the first example we talked about where the integrand was just cosine.
Okay. So in the first example where we had cosine, if I go all the way back to there, yes. So you're saying, is it necessary for the oscillations? So there's no point of stationary phase in this example because the oscillation frequency is just this constant omega everywhere. Right, so this function you could think of as sort of having a psi of t, which is omega t. And if I take psi prime, I'll just get omega. And you can see it has a constant oscillation frequency. The period is the same everywhere. So yeah, this issue doesn't arise in this setting. It's really for systems where the oscillation frequency does slow down and actually comes to zero frequency at some point, which is what we're seeing now when psi prime is zero at places like this or, like this. So anyway, if we have the second derivative, but not the first being, or sorry, I said that backwards. If the first is zero, first derivative is zero, but second is not, then the contribution coming from that quadratic term in the Taylor series will end up giving us this scaling. So I'll show that momentarily. But you might wonder, what if I have a few derivatives equal to zero? I mean, those cases can be handled. I don't think we're going to discuss them in much detail, if at all. But in these non-generic cases where if, let's say, psi prime is zero, and also what if by some miracle the second derivative is also zero there, but the third derivative is not? Maybe you can guess what will happen. Your pattern recognition abilities may be kicking in here. You'll get that the integral is of the order of x to some power. Anyone want to guess what the power will be? Maybe type it in the chat if you have a guess. So as a reminder, we had 1 over x for the vanilla case. For a typical stationary phase, we had 1 over x to the half. Looking at the chat, everyone's guessing the right answer. Yes, x to the minus 1/3. Right, it goes down like 1 over the cube root of x rather than 1 over the square root of x. And so on. So that 3 is related to the fact that the third derivative is the first one that's not zero. Okay, so you get the pattern. Good. So let's see how this goes. So now I want to do our juicy example, which is to use these ideas to crank out the asymptotics for the Bessel function J0 at large x. And so we'll have some integrals to do. All right. So Bessel function J0 of x as x goes to infinity. If you have some experience with Bessel functions from a differential equations course or from electromagnetism courses or studies of diffusion or heat flow or wave propagation of any kind, elasticity, whatever, you may know that Bessel functions sort of look like sine waves and cosine waves, except that they decay as x goes to infinity. So they look like damped sine waves or cosines, but they don't damp exponentially. They damp algebraically with respect to x. And given what I've just told you about how in stationary phase we tend to get 1 over square root of x, in fact, the Bessel function will decay like big O of 1 over square root of x as we go out to infinity. But with our techniques, we'll actually be able to calculate the prefactor, not just the decay rate. So let's see how it goes. I've mentioned earlier that there's a neat integral representation for the Bessel functions. And in particular for J0, the Bessel function is this nice looking integral. J0 of x is 1 over pi, integral from 0 to pi, cosine of x sine t dt. That's something that we'll derive in a later lecture from the differential equation itself, because you may be wondering where do these integral representations come from, so we'll discuss that later. But for now, let's just take it as given. Okay, so there's my formula. And we're interested now in the large X behavior of this. Okay, so as X goes to infinity, J0 is asymptotic to what? Well, so one thing we could notice, if we want to put this in the form of the types of integrals we've just been doing with the e to the ix psi, is that observe that J0 of x is the real part of 1 over pi, integral from 0 to pi, e to the ix sine t dt, where all I'm using there is the fact that e to the I something is cosine something plus I sine something. And here the something is x sine t, this argument. And we only get the real part to pick out the cosine. So with that in mind, you can now read off that this plays the role of the phase function, x sine t. And so for our calculations, psi of t, I guess I don't put the x in the sign. So let's go back. It's just psi of t is sine of t for us. And if we look at its, are there any points of stationary phase? Well, psi prime of t is cosine of t, and that equals 0 at t equals pi over 2, which you can see is sitting exactly in the middle of this interval of integration. We're going from 0 up to pi. So halfway along at pi over 2, we have a point of stationary phase. So that's occurring in the middle of our domain of integration. Okay. Well, so now what do? We're going to expand psi in a Taylor series around the point of stationary phase, because remember I said that one point will dominate everything in the integral. So let's try this now. So Taylor expand about this point. Taylor expand the phase sine of t about pi over 2, and you get sine of t is sine of pi over 2 plus the derivative of sine is cosine. Evaluate that at pi over 2 times t minus pi over 2 plus take the second derivative of sine, that's now negative sine. So I have plus, I'm supposed to do, so the negative sign gives me a minus, then I have 1/2 because it's a Taylor expansion, so I expect 1/2 f double or psi double prime. So 1/2 sine at pi over 2, and then t minus pi over 2 all squared. And plus dot, dot, dot. So when we simplify this, of course, cosine at pi over 2 is 0. We're not surprised. That's the point of stationary phase. This sine of pi over 2 is 1. And so this becomes 1 minus 1/2. This sine of pi over 2 is 1. So I have minus 1/2 t minus pi over 2 squared plus, I'll ignore the cubic terms. I don't need them. Okay, so I have that. And now let's put that in the integral. All right, so then the idea is that as x goes to infinity, the integral we're interested in, we'll take the real part later. For now, let me just work with 1 over pi integral e to the ix sine t dt from 0 to pi. So I'm just going to respond to something in the chat here. Let's see, it should be 0 to pi. Did I make a mistake somewhere? I said up here in the middle of 0 to pi over 2. Thank you. Good, appreciate that. I think I've caught the mistake. All right, great, thanks. Yep, so as x goes to infinity, this integral is going to be asymptotic to what I get if I just keep up to the quadratic term in the exponent. 0 to pi. So now, oh, actually, let me take that back. Since I want to focus on what's happening in the neighborhood of the point of stationary phase, what I can do is, rather than say 0 to pi, I'm just going to go in a little infinitesimal neighborhood of this. So I'll go from pi over 2 minus epsilon to pi over 2 plus epsilon. And then I feel like I'm running out of room on the edge of my page. So I'm going to just move this down. Let's put this down here. This will be asymptotic to e to the I x. Then put in 1 minus 1/2 t minus pi over 2 squared, dot, dot, dot if you want, but we're not going to use those, dt. And yeah, so I just have this kind of contribution coming from that one point. Now that's looking a little bit messy. So let me just clean it up a little bit. Let me take out the constants, 1 over pi. There's an e to the ix that doesn't depend on the t. Then I'm going pi over 2 minus epsilon, pi over 2 plus epsilon, e to the minus ix over 2, and then t minus pi over 2 all squared, dt. And so we have to contend with this integral that's sitting here. And so let me do it by changing variables. I'm going to say let's introduce a new variable s. What I want is I want the exponent to be just is squared. I want it to say e to the minus is squared. So I'm going to let s equal x over 2 square root times t minus pi over 2. So that's my change of variables in here. And so my integral is going to then become two over x. So here's why I did that. This becomes very nice and clean. I get 2 over x under a square root, 2 over pi. No, actually, let's take that back. Let's just keep the 1 over pi for the time being. 1 over pi, e to the ix. So I'm just copying from up here. 1 over pi, e to the ix. I've cleaned up this stuff with this change of variables so that it has now become integral. And here comes a little surprise. What used to be pi over 2 plus or minus epsilon is now going to become minus infinity to infinity. And I'll explain why in a second. And then the whole point was that this integrand is now nicely cleaned up to just e to the minus I s squared ds. So let's try to understand what just happened there. First, let's focus on what's in the box. The limits of integration, if I make this change of variable that I have in the box, suppose I put in t equals, say, pi over 2 plus epsilon, then I'm going to get a square root of x over 2 times an epsilon. And now here's the interesting thing. Think of epsilon as a small number, but fixed. Meaning it doesn't depend on x. So I just take some tiny number and I look at what's happening in the neighborhood of the point of stationary phase. And so this term is sort of the order of, this is of the order of epsilon. But the interesting thing is that then when I let x go to infinity, which is the limit I'm interested in for my asymptotics, you can see that this limit up here in the integrand is going to correspond to s going to infinity because of the x going out to infinity. It's this interesting stretched variable where I've taken the little neighborhood of the point of stationary phase and I've blown it up to be the whole real line. So the limits become s between infinity and minus infinity, since we're taking the limit as x goes to infinity with epsilon fixed. So that's very nice because with these, by doing the integral from minus infinity to infinity, it's a definite integral that is known. It's closely related to Gaussian integrals. It's kind of like an imaginary version of a Gaussian integral. So in fact, these integrals are tabulated. And let's see how we're doing on time. I might want to work it out with you using complex analysis. It's a nice little contour integral that we could do. But let me not do that yet because I want to focus more on the asymptotics and the method of stationary phase. So so we can show that this integral equals, it turns out, to be square root of pi over 2 e to the minus I pi over 4. And so maybe if we have time, we'll do it. But this is actually a very nice thing that goes in the literature by the name of Fresnel integrals. If you look at the real and imaginary part of this identity that I just wrote down for that integral, it gives you these cool facts. That integral from, oh, wait 1 second, I made a mistake here. Oh no, I'm good. Well, okay, I'm a little bit off. Wait, I better be careful. Hold on 1 second. Yeah, I've skipped a step or two, too many. Let's see, I think everything I've said is okay, except, let me take this down and hide that somewhere. Here's what I wanted to do. Rather than do the integral from -infinity to infinity that I've written here, let me do twice the integral from 0 to infinity. So I've got 2 over x. This is now a 2 over pi. The e to the ix is just sitting there. I'm going from 0 to infinity now, because the integrand is even in S. So I haven't done anything tricky there. I just went from 0 to infinity instead of -infinity to infinity. But the reason I did that is because these are the known integrals. It's otherwise I'd be off by a factor of 2. So the results are that if you go, say, cosine, oh God, if I do cosine of s squared ds from 0 to infinity, you get, well, I should be able to read that off. I also get one for integral from 0 to infinity, sine of s squared. I haven't written them down, but I should be able to see what they are. Let's see. It looks like, what should it be? This factor of, assuming the line above is right, looks like I should get square root of pi over 2 and then e to the minus I pi over 4.
1 over square root of 2.
That's down here, right? Yeah. So, I mean, it's got to be square root of 2 over 2, right? So then that simplifies. Square root of pi all over 2. Have I done that right?
Yeah.
I hope that's right. I think that's right. Okay, I'll return. It's possible I'm off by a factor of 2 or something, but I think I've got it right. I could quickly open up Mathematica. Let me screen share for a second. I'll stop sharing this. Let's get Mathematica open for 1 second. Yeah, I wasn't planning to do this, but we can do it. Why not? Wait, have I shared my desktop yet? Yes, shared desktop there. This was unplanned, but I'm a little flustered by being off. So let's see if Mathematica knows how to do this. Integrate. How about cosine s squared, s going from 0 to infinity. That's not what I had written. It's interesting. Oh, I see. It's because what I wrote was a little bit off. Good. Now it's better. So let me, yeah. Okay, let me correct this on my page. Okay, not share this. I'll share, go back to the pad. So I think I've corrected it now. This is what Mathematica told me. And I think what I did was I made my square root a little too big. If I had written it like this, then it would be right. The 2 is not inside the square root. Okay, yikes. Anyway, so let's suppose that this is now finally figured out. And so where am I? I guess what I've been trying to do this big long chain of everything that I've been interested in was this asymptotic formula. So assuming that I now have the integral correctly, I'm getting square root of 2 over pi x e to the I x minus pi over 4. Where the pi over 4 is coming from that e to the negative I pi over 4 that I had in this formula above. And so now, remember, this was something I'm supposed to take the real part in the last step to get what I'm interested in. We had been working without doing the real part. So taking the real part, right? I mean, let's just go back up in the chain of reasoning. All these asymptotics are for this expression, which is the thing whose real part is what we're interested in. Okay, so taking the real part of this answer, I get that J0, according to this, should be 2 over pi x, all inside a big square root, cosine x minus pi over 4. As x goes to infinity. Okay, so I wanted to see how good that was or not. And so I before class started, I checked this out in Mathematica. And here's what I got. So J0 is shown in blue. And the asymptotic formula is shown in sort of orange or yellow or whatever that color is, tan. And at first I thought Mathematica was doing something wrong, or I was doing something wrong because I didn't see any blue. But of course, you probably know what's going on, which is that the blue is so magnificently approximated by the asymptotic formula that it's covered. So that becomes a little more clear. Instead of going from 0 to, I mean, if you see what I've done in this picture, I'm going out to x equals 100. Here's what happens if you just go out to x equals 10. So again, you can't really see the blue underneath the orange until you're really, like now you can, right? There's a little departure because the 1 over square root of x business is blowing up in the asymptotics as x goes to 0, where it has no business. You're not supposed to use the asymptotics as x goes to 0. This is an x goes to infinity asymptotic, whereas the Bessel function is equal to 1 at 0. So they don't agree very well there. But man, oh man, like they're already hugging each other when x is like on the order of 1. Now this is crazy. The theory was developed assuming x goes to infinity, and yet it's working magnificently for x of order 1. So this is the kind of miracle that can often happen in asymptotics, and I don't really have a good explanation for why it's working so well. It just did. All right. So, well, I guess the question is what to do next. I prepared a couple of things. I have a couple more examples. I think that's a better use of our time than doing the contour integral, much as I like doing complex analysis. I think it's better to show you some asymptotics. So let me just finish with this. I mentioned a caveat, which was that what happens if the function itself vanishes at a place where you have a point of stationary phase? Then something else could happen, right? Because the modulation has shrunk to 0 at the same place where you're expecting the maximum contribution to the integral. So who knows what will happen? So here's a little cooked up example to explore that. Suppose this is the function we're integrating. So here the psi, the phase is t squared, but it happens to be 0. Its derivative is 0 at t equals 0. The same place where this modulation happens to be 0. So we might expect we will not get the predicted 1 over square root of x as usual. Scaling. And actually, this example is so contrived that we can just do the calculation exactly. You can probably spot that this term in here is an exact differential. Right, this t is related to the chain rule factor that would come from differentiating the t squared. So, in fact, if you just take d dt of this whole expression, e to the ix t squared, and then divide by 1 over 2 ix, you get the integrand, or divide by 2ix, you get the integrand, exactly. So this is an exact differential, and what we get is that the integral is this expression evaluated at the boundary, which comes out to be 1 over 2ix times this term. And so in fact, in this case, we're getting order 1 over x rather than 1 over square root of x. And this is exact. It's not just, this is an exact formula, not just asymptotic. But it's showing that you can have a faster decay than you might otherwise. One last example is just a little further warm up, or a little more exercise. Suppose we had something like this, a little more complicated location for a point of stationary phase. I've got cosine of x, but now my phase function is t cubed over 3 minus t. So here I'll just blow through the calculation. You could read it on your own time if you want to go slowly, but it's just to make a point of that we can exploit the fact that we're getting the contribution from the neighborhood of 1 point to sometimes conveniently push out an integral all the way out to minus infinity and infinity. So watch how it goes. Here I've got cosine of something that's rapidly, that's large. I've got that phase term, stationary phase when d dt of that argument is 0. So that's when t squared minus 1 is 0, which the only point of interest is t equals plus 1. T equals minus 1 would be outside the range of integration. So looking in the neighborhood of t equals 1, I could expand this phase function into its quadratic Taylor approximation. And then if I just plug that in, I have cosine of everything's being multiplied by this x, so I get minus 2/3 x plus x t minus 1 squared. And then by doing a this is where I want to do this clever move. This is asymptotic anyway. So if I'm only interested in the leading term, not the whole asymptotic expansion, just the predominant term, there's no harm in extending the range of integration all the way out to minus infinity, rather than just going from 0 to infinity, because I'll just be adding terms that would affect higher order asymptotics, but not the leading term. So why did I do that? Well, it doesn't affect the leading term, but it has the advantage that then I can replace the t minus 1. Everything's being centered around 1 at the moment. If I replace the t minus 1 by a t in my integral, just change variables, like say t minus 1 equals s, and then call s t, then you have the very convenient integral being centered at 0 and going from minus infinity to infinity. So now we have this where I've used a trig addition formula to expand this cosine of a sum. So I have a term that depends on x, an integral, another term that depends on x, another integral. And those two integrals are related to those Fresnel integrals I mentioned earlier. So they can be read off. They're both turn out to be pi over 2x square root. And finally, you can recombine everything back into a nicer expression using the trig identity in reverse. And you end up getting that this I of x is pi over x square root cosine with, again, a pi over 4 phase shift. So this is the kind of wheeling and dealing you can do with the method of stationary phase. There are better methods. This method only gives you the leading term in the asymptotic expansion. Next time we'll see how using a more sophisticated technique, the method of steepest descent, will let us get as many terms as we want in these rapidly oscillating integrals. Okay, so I think I will quit there. Thanks very much. Okay, so I realize I was blazing. If you want to ask any questions about anything, we can do that now.
In this last example, isn't it the case that there are stationary phases at t equals 1 and t equals minus 1?
You mean now that I've done this trick with extending the range of integration?
Yeah, right. So my concern is that, so when we compute where the stationary phases are, we have t squared minus 1 equals 0.
Right.
And so t equals minus 1 would also be a stationary phase. So when
It
we
would,
extend,
but
when
it's
we
of course
extend
it's
the
not in
domain,
this. It's not in that domain.
But it
But
becomes
then-
in the domain when we extend it, right?
Right. But the thing is that so it's true, but it's not a point of stationary phase for this. I mean, now that I've made this Taylor approximation around the 1 point, the only point of stationary phase, now that I've done this, is the one at t equals 1.
Oh, okay, I see.
You know, so because whereas I had a cubic that had the 2 points of stationary phase, this thing only has the 1 point of stationary phase. Right, I'm only, you get the idea. I'm just looking in the neighborhood of that 1 point. So having done that, then I can, with total abandon, stretch out my integral from minus infinity to infinity with no harm done.
I see.
Yeah, so it's just, the reason for doing that is it lets me get an exact prefactor by exploiting these Fresnel integrals. Otherwise, I'd have some awkward integral that I don't think I could do exactly that's centered around this t equals 1. Yeah.
So if there are multiple points of stationary phase within the domain of integration, would we just split the integral into, say, 2 integrals and do
Yes.
this method around
Yes,
each one? Okay.
exactly. You do it around each one, and then you'd see if they have the same order of magnitude or if one dominates the other. So we'll see calculations like that. I think maybe even in the next lecture, where we'll get a contribution from 2 different points, and one of them will turn out to dominate the other. But you know, yeah, you could certainly have, like in this problem, if I had done the integral from negative infinity to infinity, if that were the question, then I would get a contribution from both points of stationary phase. And I think they would contribute the same amount. But yeah, in general, you'd sum over all the points of stationary phase. But you do have to check, are they giving you the same asymptotic size or not? They, like one might correspond to something that's a second term in the expansion of the other or something. It just depends on the details. So I didn't have time to show the contour integral in our class, but I don't know, would you like me to just give you a little hint about doing it if you want to do it for fun? Sure. So, yeah, I don't know if I'll include this in the, I guess we're still recording. I could potentially include it. Yeah, all right. Why don't I just write it down for anyone who's curious? I mean, well, all right, I can show you the details, or I could leave it as an exercise, but if we did want to evaluate, let's call it I1 equals integral from 0 to infinity e to the minus is squared ds. A convenient contour for doing this. So here I'm assuming you've had enough complex analysis that you know what I'm talking about. So use this contour in the XY plane. So here's, or actually I should say SY plane. Let's draw something like that. And then out to some distance R, then go straight down. And then go till you hit the 45-degree line and then draw this. So I'm going to call this curve gamma 1 going like that. This point down here is at minus IR on the imaginary axis. This will be called gamma 2. And we could, depending how you want to do it, we could close it, we could close the contour, or we could just equate these two integrals. That is, if I compute the integral on each of those curves, then, so the integral on curve 1 plus the integral on curve 2 is going to be the same as the integral along curve 3, because they join the same points in this function e to the minus iz squared. That's analytic everywhere. And that's an entire function. So, I mean, other than at infinity, but in the finite complex plane, that it's analytic everywhere. And so by Cauchy's theorem, these integrals are equal. Or if you prefer, you could say go around the closed triangle till you come back to the origin. That integral will be 0. It's equivalent to saying what I just said. Now, so what's the point? So I1 is the integral we were interested in. Well, I'm going to take the limit of capital R goes to infinity. But so I1 is the integral over gamma 1 of e to the minus is squared ds equals the integral of interest as R goes to infinity. And I2, we're going to show goes to 0. So that won't contribute anything. And I3 can be evaluated exactly in terms of a Gaussian integral. Or a gamma function, or whatever you want to call it. So, let's see here in the chat. Gamma 3 is oriented backwards. Right, so this is the question. The way I've written it, I oriented it the way I meant to orient it. That I'm saying the integral between these 2 points here and here is independent of path. So I can either go this way or I can go this way. All right, Cauchy's theorem is usually phrased in terms of closed loops. So you could phrase it this way, that this integral plus this minus, going backwards on gamma 3, that will give you 0. Anyway, either way, it's the same thing. But so I guess the question is, should I keep doing this? Do you want to do it or you want me to do it? I think you would find it fun to do. But I guess let's put it this way. If you would like to do it, this is a good time to leave. Like you could just say, see you later, and turn off your Zoom.
Okay, thank you.
Sure, you're welcome. So maybe for someone who would like to see it, I'll keep going. Why not?
I don't have much experience with this, so I'd be interested in seeing it.
Sure, okay, that's perfectly fine. So yeah, I mean, you'll need to take a complex analysis course to learn what we're talking about in detail, but just to give you the flavor of it. I mean, the main thing is there's this big result that when you have a function that's analytic, meaning that its derivative exists in the sense of complex variables, that you define, well, I shouldn't try to teach the whole course right now. But anyway, you'd have to learn what it means to be analytic, and then the integral of an analytic function around a closed curve is 0. If it's analytic on the curve and inside. So this function has that property. And so then what you do in these problems is compute an integral you're interested in by comparing it to one that you can compute, which is going to be this one. And they differ only by something that's going to turn out to go to 0. So anyway, let's just do some of the steps. All right, so I3, I say, gives us a Gaussian integral. So you have to parameterize that curve gamma 3. That was that diagonal line going down. On the curve gamma 3, z is of the form r e to the negative I pi over 4, where r is running from 0 out to capital R in polar coordinates. I'm going to just sort of think of r going to infinity. I might be a little loose with that. But anyway, that's the parameterization. And so then you have to substitute for, so the integral on gamma 3 of e to the minus I z squared dz becomes, well, so we take this parameter little r out to infinity. We have e to the minus I. The z is r e to the minus I pi over 4. That's all getting squared. The dz would be dr e to the minus I pi over 4. All right, that's my dz. And then you have to clean that up a little bit. So factor that out. E to the minus I pi over 4. Integral 0 to infinity. And what's so cunning about this is that when I square that e to the minus I pi over 4 up in the exponent, watch what happens. I have e to the minus I r squared. And then this becomes e to the minus I pi over 2 up in the exponent, dr. But e to the minus I pi over 2 is negative I. Right, that's because on the unit circle, that's down here. So that's minus I. And then that minus I times the other minus I in the exponent.
Oh, that just gives you a negative or a 1.
It gives you a thing you see in statistics.
Right.
Right? That gives me an e to the minus r squared dr.
Oh, and now we have a Gaussian integral.
And that's the Gaussian integral. And so if you wonder, why did I choose that particular strange path? Why did I do that? The reason for choosing the gamma 3 is because when this angle gets squared, it gives me this angle, which gives me a negative I, which is exactly what I need to get a Gaussian integral that converges.
Right.
You know, so like if I had picked the triangle up here going this way, that would be the wrong triangle because I'd get an e to the positive r squared. That'd be no good. So you have to pick a clever contour, which is what we just did. So anyway, this is a known integral. And so this gives us e to the minus I pi over 4. And then this is square root of pi over 2. That integral. So that's cool. And then we have to show that I2 goes to 0. That contribution from the side, this one, is negligible. And that's pretty straightforward also. So that requires a little bit of skill in analysis. What you could do is just calculate it. Here you have to estimate it. You're not going to calculate it exactly. So I2 is the integral over gamma 2 e to the minus iz squared dz. Now the parameterization of that path is z is of the form, it has a real part always constant r, right? Because I'm over here at r. So I'm staying at a constant r, but I'm descending in y. So I could write it as z equals r minus iy, where y goes from 0 out to infinity. Well, I'm really should be going out to r, but I'm going to then take r to infinity momentarily. So anyway, do that. Now substitute in. So you get 0 to infinity e to the minus I. Squaring the z, I get r squared minus y squared minus 2ir y, all up in the exponent, times minus I dy. That's my dz. And so
do you get a plus
yeah.
y squared? Oh, no, I'm sorry. It's because
right, because you're squaring
okay.
the whole quantity iy squared. Right.
Yeah.
Right. So that's why it's a negative. So then we're interested in the magnitude of I2 because we want to bound that and show that it can be made arbitrarily small. So that's less than or equal to, there's a standard trick in complex analysis, which is if you want to estimate the magnitude of an integral, it's less than or equal to, it's basically a triangle inequality. Rather than take the magnitude of the integral, you compare it to the integral of the magnitude.
Right.
If you take the integral of the magnitude, that has to be greater than or equal to the original integral because you have no chance of cancellation. So here we could look at the magnitude of e to the minus I r squared minus y squared. And then there's a term e to the, so magnitude of, let's see, I have to multiply those two negative signs and the I squareds, I get minus ry times 2. Let's be more careful there. Minus 2 r y. The magnitude of I is just 1, so dy. So that's a bound. And actually, this thing lives on the unit circle. This is e to the minus I times something real. So this has a magnitude of 1, which is all I'm interested in, its magnitude. So it's really nice. I just get that this is less than or equal to the integral from 0 to infinity of e to the minus 2ry dy. And that's an integral I can do. This gives me e to the minus 2r y over 2r, negative 2r, from 0 to infinity, which is 1 over 2r. And that goes to 0 as r goes to infinity, which is what we're interested in. Right, we make the triangle arbitrarily big. So that's basically the idea. We can show that I2 can be made arbitrarily small. I1 is the integral we were interested in, and we now are equating it to this integral I3 that we calculated. So that's the argument.
So we defined R as the length of the vertical leg of the triangle.
Yeah, so we did a triangle with, it's a right
right.
isosceles triangle. We integrate out to a place, capital R, and then later take the limit R goes to infinity.
Okay.
But when you get good at this, you can just sort of set R equals infinity in your mind to begin with. But strictly speaking, you should just do a triangle and then take R to infinity later. Yeah, so it's very clever. I mean, the whole thing with contour integrals is figuring out the right shape to integrate around, where you build in the integral you're interested in, some piece of the real axis, and then some other stuff that hopefully has good properties. Okay, so that, strictly speaking, isn't really part of this course, but hope you enjoyed that.
Oh, yeah, thank you. Thanks for sharing that. I appreciate it.
Sure, you're welcome.
Are you planning to post this document as well? I'd like to go through it again.
Oh yeah, so the lectures are all posted on our page.
Okay.
If you go to the Canvas site and look at pages, I have the Mathematica notebooks and the lectures there. One for each lecture.
Okay.
All right. Okay, Sarah.
Sounds good.
See you later.
Okay. Thank you.
Bye. You're welcome.